Hello everyone, I'm Yegor from Gravity Engraving, a channel about laser machines and markers. Today we're talking about 3D engraving inside crystals, a topic I've covered before. Unfortunately, some people watch my channel but don't listen to what I'm saying. Everyone thought I was saying no one had ever done this before, and I was the first. No guys, the point was that no one had done it on UV lasers before. So about a year ago, they started doing these things on UV machines. And just so you know, these machines are much cheaper than, say, a green laser, and they do the same thing with better quality and detail. We'll look at it in depth, I'll show you, and then we'll move on. Unfortunately, I'm a bit cramped for space today to show this equipment from all sides. We're in a workshop where they test, assemble, and demo machines. We're connected to a chiller, which is included. It's for cooling the source, which is a UV radiation source. 5 watts. The machine has a stepper motor on the Z-axis with an encoder for precise positioning and setting the correct engraving level. It has a built-in tracing beam, galvo scanner, and a 70 by 70 lens. Inside, we have power supplies and the controller itself. It's a licensed controller with its own software. Regarding the software, there's a tutorial video. I've posted it on YouTube and I'll put it on Yandex Disk too in the Telegram channel, so everyone will have access and can use it if needed on how to install, connect, and start it up properly. It works via RJ45, so no USB cables are needed. It's all very simple and convenient. The software's internal features allow for both 2D and 3D work. We're currently in 2D mode. We load any image and apply a fill. It allows us to use various filling methods. Everything is clearly labeled, shown, and visually demonstrated. You can also load photos, meaning raster images or vector images. There's an option to use a plugin for 3D engraving. It's a completely separate plugin where you load STL files. Let's take one of the models. I'll show you how it's done, and then we'll go through the process together. Well, let's do Dobby. The model's loading. We can rotate it however we want and change its size proportionally. Change the size proportionally to fit our square, our cube. This is a 50 by 50 cube. Press enter. Scale Dobby proportionally. Set the value to 0. 0.5. That way, Dobby fits perfectly inside our cube. One thing, don't put the image in a corner if you're doing a single image without changing its dimensions or size. Now, if you're doing a mass quantity of images, then yes, it makes sense to place them anywhere, but that's not needed here. The next step is, accordingly, to generate the object for 3D engraving. It'll be used in warm tones so that the program understands which contour starts being engraved at what moment, sequentially from the bottom up. We can also change the laser parameters on the right side. We can change the laser parameters on the left side directly related to the engraving itself, like the number of layers, steps, and processing. So all of this is set here without any issues. We set the focal length, meaning we place our cube, and accordingly we start testing it in the engraving process. And we move either higher or lower to get a sense of it. Here we can now reset it or set it to a 0 value. We recently did a test, literally on glass inside glass. Actually, we set the value to 0, raise the head higher, and move on to the process of setting the focal length and the actual engraving. After setting the focal length, you must press the red beam. The red beam is traced with our object. We set it in the area where we plan to engrave. In our case, it'll be the bottom left corner. And after that, all that's left is to press F2 for engraving. Let's look at a few points and then go see the model more closely and in more detail. In this part, what I like is, here we have the file log, which records the layer and time. Everything necessary will be fully documented here. Plus, this can be repeated if you haven't moved the model. That's one thing. Next, let's look at the right panel. What you should also pay attention to, and what we're about to get to, are the factors regarding quality, brightness, dimness, and everything else. The UV laser has a very thin beam, so it's important to understand that when we chip the glass, we get a very small fracture. So the 355 nanometer wavelength is thinner than the 532 nanometer one by almost twice as much. So the XY interval is the oscillation interval of the wobble mode. So you have to consider that with this oscillation, the smaller the oscillation, the smaller the point, and the lower the detail will be accordingly. Meaning the detail will be better, but you'll also be burning the glass more. If you set the detail to a higher value, say 5 or 6, making these kinds of circles, the detail of your object will decrease. I'll do another version now with a higher fill density, or rather a higher oscillation density. Now, layer thickness. The layer thickness will actually determine the brightness of your layer, how saturated it is with white or a milky transparent color. Let's say, well, plus the Z interval, every step we also do a Z interval. Next point, I also thought it'd be better to make it more powerful, but more power didn't seem so good. Look, we have power, it's not adjustable here, and there's frequency in kilohertz. So we select it from the table in relation, again, with the pulse width, which is measured in nanoseconds. And the lower the pulse width goes, meaning the shorter the pulse width, the higher the machine's power output will be. So let's say we take it at our layer thickness. When we hit a single point with a focused beam using short pulses of 10 or say 15 nanoseconds, the pulse should be enough to break the glass right there. As soon as we hit it with 1 nanosecond pulses, 1 nanosecond, that's a short but very powerful pulse. And when focused, the glass cracks along the length of our focal distance. So if we're hitting glass that's on average 0.04 or 0.05 millimeters thick, then when engraving, at 1 nanosecond, we engrave the glass up to half a millimeter, even a millimeter. We can engrave it and the glass gets scorched to a yellow state. Now let's look at the model and see what the overall result is. Okay friends, let's start with last year's blanks that we made back then. Right to the details. Last year we used a standard screw, meaning it was a Z-axis stand with a regular screw. Nothing fancy. You can see right away there are lines. So when turning the screw half a turn or a quarter turn or a full turn, this kind of line appears. It's bound to happen. You can't avoid it. Notice right away there's this shape inside the head. That was an internal part of the STL model, so it was also engraved because the model is split by outer contours. I'm using wipes because I know people will start writing to me, you touched it with dirty hands, smudged it all, it's filthy, can't see a thing, so I wiped it with alcohol for you, found some wipes and alcohol and got it done. So that seems clear. Don't skimp on screws. Use ball screws, specifically ball screws, meaning proper guides and proper screws. Let's take the next blank. This one was also made, I think, on a ball screw machine, a proper one. Basically, there were all sorts of tests from last year here. Well, some are okay, some are not. The models were again from freestl.ru. The detail is, well, not bad, but last year we were just playing around. Nothing more, just testing. Let's set that aside and look at today's models, the ones we made. Specifically on a proper ball screw machine, and the issues you'll face, I'm telling you now. In these models, everything that could be squeezed out, I squeezed into the model on the right. That is, the detailing of the back, let's change the light, let's do it from the other side, from above, from behind, from the side. So actually, to see all the detailing, here it will be clearly visible right here. You need to engrave with very, let's say, precise parameters. That is, with a density of approximately 5/100ths of a millimeter. The step is also about 5/100ths of a millimeter. We get good maximum detailing. Accordingly, the model looks good. It glows well. It also looks quite good. If we consider the models in economy mode, the economy version that is, in this model you can see very clearly that we have exactly, due to the fact that the beam was slightly higher in power and pulse strength, it blurred to a greater depth. unlike the model on the right. Well, just to demonstrate this to you a bit so that you can see it all really well, as clearly as possible, let me do it like this. Look closely at the chin. The camera doesn't even focus on the central dog. Now, unfortunately, that's a fact. We flip the model to the little doggy, it's detailed to the max, so everything is visible on it. Everything's detailed, everything's cool, everything's good. Same thing from this angle, the same dog will be completely fine. Everything will be done well. Again, provided that it was made at about 4/100ths of a millimeter in density in the height of the pass step line. Here, we already decided to test the option with a beam oscillation of 8/100ths of a millimeter, and we got a minimally saturated image. Yes, it doesn't turn yellow like the one on the right. It doesn't turn yellow, obviously, just like this one practically doesn't turn yellow either. But despite that, its detailing is, well, as minimal as possible because it was made with very large oscillation lines. So it's more or less clear. The same story here with Dobby. With Dobby, there are key nuances. The first nuance, the model's assembled from several options. First, we did the bottom layer at high power, so the beam, specifically at the focal distance, went through too much depth, up to 1 millimeter. Same as, say, the image down here. If you pay attention, it's engraved, this image right here. The thickness of this image is approximately 0.8 millimeters. It's a very thick layer. So roughly speaking, it turns out to be almost, let's say, 16 times thicker than our layer. In any of these images, 16 times thicker. Therefore, burning at high power won't work here. Unlike those same green lasers, engraving happens specifically by splitting large layers of glass. And accordingly, you get something like, let's say, a large crystal lattice, where again, on a green laser, it all looks supposedly brighter because it's easier for the eye to catch on bright crystals of light than to catch on such thin, small crystals of light. That is, when engraving with a UV laser, we get finer detailing. And here's the final result. I have achieved the maximum, let us say, optimal image detail. So its appearance, let us take a look now. It turned out as good as possible, meaning we squeezed everything we could out of it. All the reliefs and details are visible to the max. If you were to write something here, I think you could basically write characters 1 millimeter high and they would be visually clear. Model preparation, I will say right away, here for instance, the model was prepared well, meaning the model only has an outer shell, no internal connections, nothing like that, so the model engraved perfectly. If we are talking about engraving models that were originally made, pieced together from different FTLs without removing intersecting lines, then they will engrave accordingly. As for the models, I got everything from freestl.ru. There is no point in getting them elsewhere. Again, there is no point in picking models. In any case, all the models we took and used are more or less clunky in some places, and they are not suitable for this kind of engraving. I might do a photo engraving of a face in the future, but not now. I am a bit busy with other things right now, so maybe sometime in the future we will do something like that.